Okay, so first, consider this multi-loop circuit. Let's just pick some directions for our currents. Doesn't really matter the direction that I pick. I'm just going to pick them randomly. And then I'm going to choose my loops that I want to do. Notice that uh, there's no resistors in this part of the circuit over here on the right. So I'm going to choose the right loop and the big loop. Let's start here, and we'll go in that direction. So that's plus 4 minus 6 minus 2i2 equals to 0. That's negative 2 minus 2i2 equals 0. So I2 is equal to 2 divided by negative 2, which is negative 1 amp. Right. So that's I2. Now to get I1, I'm going to consider the big loop. I'll start here and I'll go in that direction. That's plus 2 minus 6I1 minus 4 equals to 0. So let's see, that's negative 2 minus 6I1 equals 0. I1 equals 2 divided by negative 6, or negative 1/3 amp. And then finally, to get I3, I want to do the junction rule. I'm just going to pick a junction. Notice I have I3 going there, I2 going there, and I1 going there. So I have I1 plus I3 is equal to I2. Those are the incoming currents. I1 and I3 are equal to the outgoing current, which is I2. I1 is negative 1/3 plus I3 is equal to I2, which is negative 1. So I3 is equal to negative 1 plus 1/3, which is negative 2/3. So now I can record all of these currents. I1 is 1/3 amp. I had chosen I1 down, so that means it's up. I2 is negative 1 amp. I had chosen it up, but it came out negative, so that means it's down. It's like all mine came out negative, actually. And then I3 is 2/3 amps. I had chosen it, down, so that means it's up. So I1 is up, I2 is down, and I3 is up. They're opposite because all those currents came out negative. All right, consider this circuit which has a charging capacitor. When is the charge on the capacitor equal to 30 microcoulombs? So first of all, this is a charging capacitor, and I want to know what is Q for it. So to find that, I can look at my equation sheet for a charging capacitor. That's going to be right here. Q equals Q times 1 minus. So I have Q is equal to big Q times 1 minus e to the minus t divided by RC. Okay, so little q is 30 microcoulombs, 30.0. Big Q, I'm going to write up here, big Q is equal to C times V. That's going to be 2 microfarads times 16 volts. So that's 32 microcoulombs. So 32 times 1 minus e to the minus t. T is what I'm looking for. R, that's 4. C is 2. So that's going to be divided by 8. R times C is 8. Now I can solve this. Let's see, 30 divided by 32 is 0.9375. Subtract 8 from both, or 1 from both sides. That's minus 0.0625 is equal to negative e to the minus t over 8. Those go away. And then I can take the natural log of both sides. So the natural log of this side and the natural log, that gets rid of that exponential. So the natural log of 0.0625 is negative 2.77 is equal to negative t divided by 8. So t is equal to 8 times 2.77. I get 22 seconds. Is that right? Yeah, 266. So 22 seconds is the time to reach that charge of 30 microcoulombs. Then also I want to sketch a graph of the current versus time for this. Now again, this is a charging capacitor, And so current versus time is the same for charging and discharging. So that graph is going to just look like this. It was a decay function. So current versus time will look like that. All right, proton approaches a wire with a current of 4 amps. In this figure, there's its velocity and the distance r from the wire. What is the direction of the magnetic field at the location of the proton? So for part A, let's first find the direction. So to find the direction, I use my right-hand rule. I find that it's into the page on this side, which is what I want to know. It's also out of the page on this side, but that doesn't really matter to me. And then I can calculate that magnetic field. B is equal to mu naught I over 2 pi r. That's 4 pi times 10 to the minus 7. My current I is 4 divided by 2 pi times r, which is 0.2. Some of these can cancel out. The pi's cancel. This 2 will cancel with one of those and gives me, so 8 times 10 to the minus 7 divided by 0.2. I get 4 times 10 to the minus 6 Tesla, 4 microtesla. All right, so that's the magnetic field. It's into the page. So that's in the negative Z or into the page. If you had this drawn correctly, I would have given you credit there too. Now, what is the direction of magnitude of the force on the proton? So V is, let's find the magnitude first. QVB sine theta, although in this case theta is 90, so that just goes away, that becomes 1. So the charge on a proton is 1.6 times 10 to the minus 19 coulombs. The speed is 6 times 10 to the 5th. And the magnetic field is 4 times 10 to the minus 6 Tesla. All right, so that's it for the force. I can just take the product of those three numbers. And I get, is that right? 3 point. No, that's not right. Hold on. All right, I get 3.8 times 10 to the minus 19. That's in newtons. And that force is, let's find the direction of that. So use my right-hand rule. I have a velocity that is to the right. I have a magnetic field that's into the page. So that means that the force is in the upward direction, or you could have said the plus y direction. Either one would be fine. Okay. And then finally, light goes from water into glass with an incident angle in the water of 30 degrees. So here I have this angle, which is 30 degrees. Here n is equal to 1.3, but here n is equal to 1.5. I can just sort of get a rough idea of what's going to happen. I want to know what this refracted angle is. But I know that since it slows down, you imagine our wavefronts, if it slows down here, that means it's going to curve around. So this angle, when I calculate it, had better be smaller than 30 degrees. We'll see if it is. 1.3 sine of 30 equals 1.5 sine of theta. So that's the inverse sine of 0.433. I get 26 degrees. So theta is equal to 26 degrees. That's the answer. And it is less than 30 as I would expect. Which of these statements about a household circuit is true? GSM also found in places where there is water. That's true. Bathrooms, carports. Circuit breaker turns off if the current exceeds a certain amount. That's true. Devices in your home operate at the same voltage, not current. Transformer outside your home converts the electricity from high voltage, about 3,000 volts, down to about 120 volts. So yes, that's true. So 1, 2, and 4. D is right. Which of these equations is correct? let's just start. So here I have 4 minus 2i1. That's starting here and going in that direction. 4 minus 2i1. So far, that's correct. And then minus 12, that's correct. Oh, but then I start going off the rails here. Minus 8i3 plus 6. Like, that's all wrong. The loop isn't closed in that case, so that's not right. Here, i1 plus i2 is equal to i3. I have i2 coming in, i1 coming in. Good so far. Oh, but I also have i3. It should be plus is equal to 0. So that's not right. 8i3 plus 6, that would be, it should be negative 8i3 plus 6. Like, see if I'm going in this direction, that would be negative 8i3 plus 6 minus 12. That's how to make that one correct. So that one's not right. This last one better be right. Let's see, minus 12, so that means I'm going to be going in this direction. Minus 12 plus 4, going around here, that's right, plus 4, minus 2i1, and then I come back. That is indeed the right answer. So number 2 is D. What is the current through the 2 ohm resistor? The current through the 2 ohm resistor is I1. So look, that's easy. I can just solve this equation. So it's negative 8 minus 2I1 is equal to 0. So 2I1 equals negative 8. I1 equals negative 4. I'm just looking for the magnitude though, so it's just that. What is the voltage after t equal 10 seconds? Well, let's just go back. This is it's going to be a charging capacitor. So the voltage of a charging capacitor is that growth function. So it's going to be V equals V naught times 1 minus e to the minus t over RC. That is equal to 12 times 1 minus e to the minus 10 divided by RC, which is 3 times 2 or 6. And then if I do that, I get 12 minus 12 times when I do this, I get 9.7. That's in volts. All right. Which of these graphs best represents the voltage as this capacitor discharges? Wasn't this a discharging capacitor? Oh no, that was a charging capacitor. So for a discharging capacitor, the voltage looks like this. That is a decay function. So that's what I'm looking for. That would be D for number 5. Wire carries a current of 3 amps in a direction that makes an angle of 30 degrees with a magnetic field of 0.5 Tesla. What is the magnetic force on a length of 8 meters of wire? So F is equal to I L B sine theta. That's going to be 3 times L, which is 8, times B, which is 0.5, times the sine of 30. It's 2412 sine 30. 6.0 newtons. So B is the right answer. And then I have a proton that has this velocity. That's my velocity. That's my angle. That's my magnetic field. And I want to know the force on this proton. Remember, force is QVB sine theta. 1.6 times 10 to the minus 19. That is on your equation sheet. That's in coulombs. It's the fundamental unit of charge. And then V is 2 times 10 to the 6. And B is, what was B? 3 times, I'm going to times 3 times 10 to the minus 6 times sine of 30. So if I do all those, I get 4.8 times 10 to the minus 19. Oops. Newton. zones. So that is B is the right answer for number 7. All right, which of these statements is true? The Earth's magnetic pole is at the geographic South Pole. That is correct. If you remember, think about the Earth, that I have a North and a South Pole, but if I think about the Earth as a magnet, that this is actually the South and the North Pole, that those two poles are switched. So the magnetic North Pole is at the geographic South Pole. That's where the penguins live. Magnetic fields are caused by moving charges? Yes. Wood is not magnetic and does not have any moving charges. Okay, so um, while it is true that wood is not ferromagnetic, and it's not magnetized either because it's not ferromagnetic, it is not true that it does not have any moving charges. So that is not a true statement. So the answer has to be B. There are moving charges in wood. It's just the magnetic domains are not aligned in these non-ferromagnetic materials. All right, what is the direction of the force that this particle experiences? Simple right-hand rule. V, our index finger goes in the direction of V. B is to the right, so that's into the page. It is a positive particle, so A is 9. And then a positive cation, or cation, an ion, is traveling in the plus x direction. So here V is in the plus x direction. Magnetic field is in the plus z direction, that's B. And I want to know the force, so if I do my right-hand rule, I get down. B is the right answer for number 10. Positive particle approaches a current-carrying wire. There's a current that produces a magnetic field, and I want to know the direction of that current. Well, look, the charge starts out with a velocity that's in this direction. That means that there must be a force that's causing this circular motion that is perpendicular to that velocity, in this case to the left. So if I can determine that magnetic field must be into the page that creates a force like this. And if it's into the page, that means that the current has to be moving to the right. It's into the page on that side, it's out of the page on this side. Which of these statements is true about a mass spectrometer? The velocity and force vectors are always perpendicular. That is true. The magnetic force acting on a particle increases the particle's speed. No, that magnetic force is a centripetal force. It does nothing to increase the speed. It only changes the direction of the velocity. The mass spectrometer can determine the ratio of the mass charge for the particle. That is correct too. So A is the right answer for number 12. Here I have a mass spectrometer, the values for the magnetic field, the velocity, and the radius of the path. Just to remind you, for the mass spectrometer, that the cyclotron equation is this: is R equals mv over qb. R is equal to mv over qb. By the way, you can derive that pretty easily. It's just that the magnetic force, qvb, is equal to mv squared over r. It's centripetal force, so that's where that comes from. So I want to figure out what m over q is. So I'll solve this for m over q. The mass charge ratio, that's going to be rb over v. R is 2 times 6 divided by 4. These aren't realistic numbers. I just made them easy so to calculate more easily. That's 12 divided by 4. That's equal to 3. So you have a mass charge ratio of 3. This is a mass charge ratio of 1 to 3, 6 to 2. Oop, that is 3. This would be 3 to 2 or 1.5, and 2 to 12 or 1 over 6. But the answer is Kaisite, which is not real. I want to organize these in order of shortest to longest wavelength. So the shortest wavelength is the highest energy, or the highest frequency, which is gamma. That gets rid of these and this one. And then the longest wavelength is the radio, but both A and B have radio, so we have to figure out the infrared and the visible. This is the right order: gamma, visible, infrared, and radio, B for 14. Photoelectric effect demonstrates that light acts as a particle. Reflection also demonstrates as a particle. Here, I want to show this reflection. This is 30. That means this is 60. That means this is an equilateral triangle. That doesn't really look like it, but the idea. And then if that's 60, that means that this is 30 and that this is also 30. So answer is A for 16. All right, which is the speed of light larger? Well, think about these waves as they come along here. They're going to slow down so it can speed around here. That means medium one has the higher speed. And then this is just like your free response. Light travels from glass to air. Uh, we're assuming that air has an index of 1. As I said, you need to know that. It's the same as a vacuum. Actually, the index of refraction of air is a little bit bigger than 1, but it's basically almost like 1.00 something. Um, so it's going from glass to air. 1.5 sine of 30, that's our incident angle, is equal to 1 sine of theta. If I solve that for theta, I get 49 degrees. Here I want to know what is the angle theta 1 for total internal reflection. Remember, total internal reflection is a special case where this angle is equal to 90 degrees. So we just say 1.2 sine of theta 1 equals 1.1 sine of 90. It's just a special case of the law of refraction. And then I solve that for theta 1. That's the inverse sine of 1.1 divided by 1.2. Which is 66 degrees. And then who is Dr. Young's favorite student? Oh gosh, this is hard. Shane Swan. Shane Swan works in industry. He ran for the state senate a few years ago. Devin Bourgeois is a doctor. He was at Family Doctor Clinic, but now he's at, I think he works at Twitter Regional now. Victoria Bourgeois, oh, she's in med school. She's super. Ashley Johnson, she was a track athlete here for some years. And I think she works in research now. I think she's the one that works in like the pharmaceutical industry. Or, anyway. So the right answer to that is E. My favorite student is you.